Hi, and thank you for joining me on Ladies in Tech. This is the go-to place for free PLC training. Make sure you subscribe so you don't miss out on a single lesson. Thank you and have yourself a wonderful day. This video is going to be, what is a programmable logic controller? A PLC is a solid-state system for control and operation of manufacturing equipment. NEMA, the National Electrical Manufacturing Association, defines a programmable controller as follows. A programmable controller is a digital electronic apparatus with a programming memory for storing instructions to implement specific functions such as logic, sequencing, timing, counting, and arithmetic to control machine and processes. PLCs replace control systems that use relays, drums, and switches. Advantages a PLC has over relays, drums, and switches style of programming is size, speed, more logic functions, more reliability, user-friendly, and lack of hardwiring, allowing frequent changes to the program. You can see here in this picture is a bunch of relays. So this is a bunch of relay logics and basically a room. So it takes thousands and thousands of relays to obtain the same logic that you can write in a program. So just the size alone goes to show you here the space savings that you would have using a PLC compared to relay logic. Relay ladder logic. It's a high-level graphic programming language and is most common in PLC languages due to the fact it's understood by most electricians because they already know relays. Other programming languages used are sequential function charts, structured text, and function block languages. RSLogix500 only has the option to program in ladder logic. And RSLogix500 would only be used to program a certain series of Bradely PLCs. A PLC compared to a computer. PLCs are designed to be operated by engineers, techs, maintenance, and require little knowledge of computers. Both have internal memory and storage. PLCs are typically programmed using ladder logic, not computer language like C++, which can be very difficult. PLCs is designed to operate in an industrial environment in a wide range of temperatures, humidity, and vibration levels and are not easily affected by electrical noise. Troubleshooting PLCs is simplified by having fault indicators, input and output status indicators, and written fault information that is displayed to the programmer. Bradely has a market share of PLCs in North America. On here we have some Bradely PLCs you may find out in the industry. We have a Compact Logix up here, we have a Slick up here, we have a Control Logix here, and we have a Micro Logix. So these are very common PLCs that you'd find in the North American market. Siemens is also pretty prominent in North America, and here shows a wide array of PLCs that the Siemens carries. You may also find Omron PLCs, they're pretty common. And other ones that are out there but not so common are Modicon, Honeywell, IPC, Texas Instrument, Festo. They all can be out there as well. PLC components. There are four major components to a PLC. First, we have the programming device. It can be handheld or a computer. These days, it's mostly computer. It is used to enter the desired program into the memory. We have the processor unit, which is the brains of the system. Next, the power supply, which supplies power to the PLC and some I/O devices. And fourth is our input and output interfaces. Push buttons, limit switches, lights, motors, solenoids are all examples of those inputs and your outputs. Let's talk about the processor unit. It is also referred to as the CPU, the Central Processing Unit. Consists of a microprocessor, memory chips, circuits necessary to store and retrieve information, and communication circuits. It is the brain. It can be a self-contained unit or may be modular and plugged in directly to the I/O rack or at a remote location. The microprocessor system is what replaces the control relays, timers, sequencers, counters, and more that they used to use. So it has all that control logic right in that microprocessor. Also too, it monitors the status of the input devices. systematically solves the logic of the user program, controls states of the output devices, communicates to all other devices on the system, and manages the memory and updates timers, counters, and internal registers. Other PLC components. We have the programming device. The programming device is used to enter, monitor, and make program changes to the PLC. It can be handheld or a personal computer. Computer is required to have a compatible software, proper communications required by the PLC. So if you go in there and you want to use RSLogix500 to program a Siemens PLC, it's not going to work. You have to make sure you have a compatible software, and as far as communications go, you want to make sure you have the correct drivers, you want to make sure your IP addresses can talk to each other in order to communicate properly on the network. The other component is our power supply. It supplies power to the control system, converts AC power levels to low DC for processor logic circuits using an internal step-down transformer, bridge rectifiers, and filters. In most cases, the power supply does not supply power to the actual input and output devices. It maintains a steady DC output voltage even when the incoming AC supply fluctuates. And then we have our input and output interfaces, referred to as I/O, inputs and outputs. It is where real-world devices are connected. The I/O cards can be modular or fixed. I/O devices can be discrete or analog. Types of I/O devices. We have discrete, either on or off, open or closed. It's going to give you a 1 or a 0 as a logic level. Examples of this are limit switches and push buttons, normally open, normally closed. Up here we have some reed switches that would be used on cylinders or slides to indicate the position of that cylinder or slide. It has a magnetic head in there so that when the magnet is close to where that slide end is, and close that switch and give you a signal. Nothing in between. Only when there's contact when that switch is closed, you're going to get a high. Push buttons, same thing, either on or off. Analog devices give you a wide range of values. They don't just give you an on or off. Examples of this are a temperature sensor or pressure sensor. They're going to give you wide ranges of voltages or current that indicates the pressure and the temperature. Discrete I/O modules. These are the actual modules that our discrete I/O connect into. They only accept a digital on-off type of signal. For example, a push button, either pressed or not pressed, is going to give you a high or a low. The module will determine the state of the real-world device and communicate the state to the processor. If the device is off and wired normally open, off or 0 is stored in the processor's memory. Available in the wide range of voltages from 120 VAC, 240 VAC, 24 volts DC, 12 volts DC, etc. You get the point. You can get them at a lot of different voltages. Analog I/O modules. Analog input modules are used to convert an analog signal to an integer value for use by PLC logic using an analog to digital converter. For example, a pressure sensor. So this pressure sensor can display a value in voltage to indicate a pressure between 0 and 100 psi. 0 to 100 psi it represents as voltage, and the voltage that it has is 0 to 10 volts DC. So at 50 psi we should assume to see 5 volts DC to indicate halfway mark. So what happens is when we only have one bit that displays 0 or 1, that's not enough resolution to indicate that there is only half of the voltage. So we use an integer value. So we can use 16 bits to display 0 to 10 volts, and when we have 5 volts, we'll display 5 on our integer value. So all we do is add more resolutions to those zeros and ones in order to obtain a value or a range of values. An analog output module changes the integer value into an analog signal using a digital to analog converter, just like the input module but in reverse. For example, this would be something you would use for controlling a variable speed controllers. So when you want a motor, we don't want to go on and off. We may want to vary that speed or maybe only run it at half speed, and what we'll do is vary the voltage out to that motor. Input and output selection. So when you're selecting these modules, there's some things that you need to keep in mind. The I/O selection is very versatile. Most any type of voltage or current signal can be changed into a logic level signal to be compatible with the processor. Things to consider are changes in voltage and current signal into a logic level signal, number of I/O needed, you want fixed or modular, digital or analog, signal needed to send to the output base based on the programming logic, you need to know what that is. Is it going to be used in a safety circuit? If it is, then we need safety circuit modules. And is it going to be sourcing or syncing? Fixed I/O. It is a complete unit containing the processor, I/O selection, and the power supply. So it's one unit. You can see in these pictures below, it's one unit. Most fixed I/O configurations can add expansion units with various I/O configurations to provide more capability of different voltages. Modular I/O. It's more flexible than fixed I/O units. It has various types of input and output modules housed in a rack or chassis. Local I/O modules mounted with the processor. In the picture below we have local I/O. You can see we have a processor here where the key switch would be and the indicators on the front here. That's our processor, this is our power supply, and this is our input and output cards. They're all next door, they're like neighbors, they're local. You can also have remote I/O in modular. So you could have your PLC and everything here, and across and down the line you can have another input card that talks on the network to this processor. So it doesn't have to be right beside it. And racks all must be configured. When you go and buy this, you have to buy the power supply separately. You need to buy the processor separately. You need to buy all the inputs and outputs. You even need to buy the end caps for these racks all separately. So you need to configure all that. So it's a little bit more work than buying your fixed I/O systems. Let's look again at our discrete input module. It can be a wide range of voltages, 120, 24 volts, 12 to 48, etc. But it's important to note is that voltages cannot be mixed. Another module or section of the card has to be used. Refer to the manufacturer manual for your wiring guide. The modules can be purchased with a variety of input terminals. Common arrangements are 8, 10, 16, 32. Even though they have more terminals, the size is always the same, the actual physical size of the card. The amount of input terminals determines the amount of inputs that can be wired. Modules can also be combo cards, meaning they have both inputs and outputs on the same card. Now below we have a drawing of a AC discrete input module. The discrete AC voltage signal from the switch is dropped to a lower voltage using a resistor. Then a bridge rectifier then converts the AC voltage to DC. Then filtering of the signal is done to condition the DC signal and protect against noise. Since electrical noise can be a short DC pulse, it can be determined as a logic level high. To protect against this, the actual input signal being sent to the processor is delayed. PLC input cards rarely supply power. This means that an external power supply is needed to supply power for the inputs and the sensors. We can see here we have an external supply. It's 24 volts AC power supply. We have a hot and our neutral. Here's the PLC card. The card itself has a neutral attached to it, so it's going to supply the common neutral. When this push button here, which is discrete, is pressed, the hot on this side will be supplied to input number 01, and it will complete the circuit because the card itself has the common. So that will give an indicator of 1 when this is pressed. So we have the positive through to the negative. And the same is true with this normally open temperature switch. So here shows you how the inputs, being this push button and this normally open temperature switch, are externally supplied voltage from this power supply. Discrete output modules. As with input modules rarely supply any power, but instead act as switches. External power supplies are disconnected to the output card, and the card will switch the power on or off for each of the outputs. Typically, output voltages are 120, 24 volts, 12 to 48, 12 to 48 AC, DC, 12 volts, and several more. Common choices of output card types are relay, transistors, or triacs. Relays are most flexible and are capable of switching both AC and DC outputs, but they are slower. About 10 milliseconds switching is typical, but it's getting better these days, much better. And they are bulkier, cost more, and will wear out faster because they are a mechanical switch. Relay outputs dry contacts is a separate relay that is dedicated to each and allows mixed voltages. So on the same card, each of the relay contacts can have their own voltage that they're switching. Transistors are limited to DC outputs and triacs are limited to AC outputs. Transistors and triacs are switched outputs. The voltage is supplied to the PLC card and the card switches it to different outputs using solid-state circuitry, transistors, triacs, etc. Transistor outputs are NPN or PNP transistors. Here is a discrete output module. You can see we have the 24 volt DC output card, and here we have an output being a motor. In this situation, this relay has 24 volts sitting here, and this output card has the common. So when this output card, this relay switches, it supplies the common, which in turn energizes this coil in this relay, causing this switch to change with the proper voltage on this motor, the 120 volts, and runs that motor. So the control voltage is only 24 volts, but through this relay that it controls, it actually switches to 120 that this motor requires to run. At this output 7, we have 0 volts sitting here and 24 volts on this other side. So when this relay switches, it has a potential difference of the 0 volts for this light to light up. So this is an example of a syncing output card. That concludes this lecture on what is a PLC. Before you go, make sure you subscribe and follow right along with me as I talk to you about PLCs and learn how to program them. Thank you and have yourself a great day.